In this video, we're going to talk about antiderivatives and indefinite integration. So let's say that you have the derivative of a function, and let's say the derivative is 3x squared. You can work backwards to figure out what the original function is. That's what we call an antiderivative. It's working backwards from a derivative to find the original function. So working backwards with the power rule, for example, with the derivative being 3x squared, we can conclude that x cubed is a possible integral or antiderivative. Sometimes we're asked to find the general solution of a differential equation. So a differential equation is our derivative, so y prime is equal to 2. It's already a function that has had the derivative applied to it, and our result is 2. So if we think backwards, we can conclude that 2x is our original equation. So we can model this here. We know for sure that y equals 2x. The derivative of that is just 2. But what if we considered a different y-intercept, like -1 or +1 or +2 or some other constant? So that all of these result in a derivative of just 2 because a constant doesn't do anything. It becomes +0. So every time you take an antiderivative, you have to apply plus c because you don't exactly know what the constant was, whether it was 0 or a different number. So that's why our solution here, our general solution, is y equals 2x plus c. In this slide, I want to talk about the notation that you're going to see around antidifferentiation or indefinite integration. So you may have seen this symbol before. It's this really tall looking S thing. And that's what we call an integral sign. So that just tells you, we're taking the integral here. So f of x is some function that we take the integral of, and that's called the integrand. And then the variable of integration, we've seen this before when we take derivatives, right? So derivative in respect to x. So that is the variable that we're going to integrate by. And this big f of x is used to denote the antiderivative, so the original equation. And then what we just talked about is plus c. So we have to take into account that there might be a number added to that equation. And here we have basic integration rules. Much like we had basic differentiation or derivative rules, integration formulas just work backwards to find the original. So for example, we had the derivative of a constant is 0, so the integral of a 0 is going to be some constant. And the rule here that produced 2 a couple slides ago, that constant multiple rule, if I take the result of that and work backwards, right, I have k times x plus c. And so all of these differentiation rules work backwards to find the integral. And in terms of notes, I would take a screenshot of this page or find it in the 4.1 part of our textbook and cut it out, paste it into your notebook so you have it. So let's work through describing an antiderivative and how you take that. So let's say you're given this original problem right here. We've got the integral symbol and you have 3x times dx. So we're looking for the original equation that when you take the derivative results in 3x. So what you can do is you can take out the constant multiple 3, move it on the outside, and that will multiply by whatever you find the integral to be. And we use the backwards of the power rule here. So it's rewritten here as x to the first. Sometimes that's really useful. And so the power rule is applied where n is 1, so that's our power. So we bump it up 1 and put it over 2. So those two things should match, the power and the number below. And so you multiply it by 3, and this is the original equation. And those steps are summarized right here. So original integral, rewrite it, integrate it, and simplify. And as you begin to practice taking integrals, I would offer for you to check. So I take my end result here, my end integral, and I derive that to see if I end up with 3x. And so that 2 comes down, multiplies by 3 halves, and those cancel to just become 3x. So I did it right. And something that's really useful, especially when you're first starting to take integrals, is to rewrite them. So here are some original integrals, and here they are rewritten to help us integrate. Much like when you took the derivative, we would rewrite some of those to help us derive a little bit easier using the rules that we knew. So for example, if I have 1 over x cubed, that's the same as saying x to the negative third power, which makes it easier to integrate and then simplify. Same thing with the square root of x, that's x to the 1/2. I can then add 1 to it and put that over 3/2, and that's how I can simplify. Same thing with a trig function like 2 sine of x. I can move that 2 out and then just integrate sine, which becomes negative cosine here, and so that makes it easier to simplify. All right, so let's work through some of these. Now, when I integrate something like there's nothing right here, I'm going to rewrite it so there's a 1. And so I have the 1 there, and so I know I need to add an x to the first power all over that same power down here, 1 plus c, so that's really just x plus c. And if I was to check that, the derivative of just x is 1. So let's move on to this guy, so x plus 2. And so what I'm going to do here is I'm going to break up the x and the 2 and integrate those separately. And now what I do for this x to the first power is I add another power, put it over that same power that's up there, so over 2, and then I add an x to this 2, so it's x to the first all over 1. So I end up with 1/2 x squared plus 2x plus c. And just like in B, I'm going to break apart each of these terms in C and integrate. So I break apart each of these terms into their own separate integral with a dx attached, and I increase that 4th power to the 5th power all over 5, and I increase that square to a 1/3 all over 3, and then I increase the x to the first power all over 2. So here's my integral for part C. So let's look at another example of an integral that I would strongly suggest rewriting before integrating. So we have the integral of x plus 1 all over the square root of x dx. So what I'm going to do is divide each quantity up top, so x and then 1 separately, divide it by the square root of x, which actually gives me x to the 1/2 plus x to the negative 1/2. So now I'm going to integrate. So here when I integrate, I'm going to add 1 to the 1/2 power and 1 to the negative 1/2 power, so I get x to the 3/2, and that's all over 3/2 because that's the rule, and then I get a positive x to the positive 1/2 all over 1/2, and so when I flip those fractions I get 2/3 x to the 3/2 plus 2 x to the 1/2 plus c. Always got to add that plus c. And here's another way that you can write that. You could take out the 2/3 square root of x and you're left with just the quantity of x plus 3 plus c. And then at this point I'm going to check, so I'm going to take this result here and I'm going to take the derivative of it, and when I do that I end up with x to the 1/2 plus x to the negative 1/2, which is one of the ways that I rewrote the original function. And an important note is that when you integrate a fraction, so when you integrate a quotient, don't integrate the numerator and denominator separately. You wouldn't do that when you take a derivative, so please don't do that when you take an integral. So this was the problem we just worked on, and here was our solution. And if you actually took the numerator and denominator and you integrated those separately, you'd actually get the wrong answer. So don't do that. So now let's rewrite another integral, but let's throw trig in the mix. So let's say I have the integral of sine x all over cos squared x dx. So the way that I rewrite this is I notice that there is 2 cosines in the bottom. So cosine times cosine makes cosine squared. So I'm going to separate that into 2 fractions that both have 1 cosine x in the denominator. So there's only 1 sine x, so that means that one of the fractions gets a sine and the other one just gets a 1, because 1 times sine of x is sine of x, and cosine times cosine is cosine squared. And so 1 over cosine is the reciprocal of cos, which is secant, and sine over cosine is tangent. And we actually have a rule for secant times tangent, so that gives me secant of x plus c. And when I check this, I take y is equal to secant x plus c. I rewrite secant as 1 over cosine, which I rewrite as cosine of x all to the negative 1 plus c. And when I take the derivative, I use the chain rule, so that becomes negative 1 times cosine x all to the negative 2 times negative sine of x, which gives me sine x over cos squared x, which is the original function I started with. Some more ways that rewriting before integrating helps you is taking out a number on the top of a fraction, right? Moving it out to the front, that's the constant multiple, and then taking something like this, like the square root of x in the denominator and making that x to the negative 1/2 makes it a lot easier to integrate. Also, when you have a binomial that's all squared, you can FOIL that out, and then you can take each of these terms piece by piece and integrate them. Makes your life a little bit easier. And something like this, when you have one variable in the denominator of a fraction, you can divide all the terms in the numerator by that and integrate a little bit easier. Also, if you have something on the outside of a quantity, you can distribute. And again, make your life a little bit easier when you integrate. So we were working with general solutions to integration problems, but there are such things as particular solutions. So in a general solution, remember we added a plus c. But to find a particular solution, we then have to solve for the numerical value of c. So let's try this out. Let's say that we're given this function here. We have the integral of 3x squared minus 1 dx. And we can use our integral rules to figure out that x cubed minus x plus c is a general solution. And so what you see here are all of the c values from -4 to +4 for this general solution. So while all of them are great, I'm going to look for one that passes through this point, 2, 4. So here's what I know. I know the original equation, the big F of x, is x cubed minus x plus c. And I know that big F of 2 equals 4, because right, 2, 4. Our input x, our output 4. So I set this thing equal to 4, plug in 2 for every x value I have, and I solve for c. And I get c to be -2. So this is my particular solution to this problem that goes through that point, 2, 4. So let's try an example where we have to find a general solution. So this is the derivative we're given. So it's 1 over x squared. We need to find the original equation where x is greater than 0, and then find the particular solution that satisfies the initial condition of f of 1 equals 0. So this is the point that we're going to plug in. So my first step is to find the general solution. So big F of x is equal to the integral of 1 over x squared dx. I rewrite it to x to the -2 dx, and I take the integral, not the derivative, and I get x to the -1 over -1 plus c, so that's -1 over x plus c, where x is greater than 0. So now I'm going to take that integral right here, so -1 over x plus c, and I'm going to use that information that I was given, the initial condition of f of 1 is equal to 0. So I set this thing equal to 0, I plug in 1 for this x, and I solve for c equal to 1. So that means that this is my particular solution, so f of x is equal to -1 over x plus 1, where x is greater than 0. Now let's apply integration to a real-world problem. So let's solve a vertical motion problem. So let's say a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. So let's find the position function, giving the height as s as a function of time t. All right, so here's what I know. I know that the height of the ball, the position at time 0 is 80, it's 80 feet above the ground, and that the first derivative, so the initial velocity at time 0, is 64 feet per second. I also happen to know that acceleration is the second derivative of our position function, so s double prime of t, and I know that acceleration due to gravity in terms of feet is -32. So starting with the second derivative, so s double prime of t, which I know to be -32, I can then work backwards to find the first derivative. So s prime of t is equal to the integral of s double prime of t, right? So if I work backwards, of dt, is equal to the integral of -32 dt, because I know that this is -32. So the first derivative, s prime of t, is equal to -32t plus some constants, or c1. And I happen to know that s prime of 0 is 64, because the initial velocity, where t equals 0, is 64. I can use this equation to figure out the actual constant, c1. So I set 64 equal to -32 times 0, because that's for t, plus C1. So that means that our first constant is equal to 64. So my first derivative, S prime of t, is equal to negative 32t plus 64. And now I can use this to find the original position function, S of t. So I have my S of t is equal to the integral of S prime of t, right? So we're working backwards to find the original. So we plug in our S prime of t, so our negative 32t plus 64, and we integrate, and we simplify to our original position function being negative 16t squared plus 64t plus some other constant, so c2. Now I'm going to do the same thing that I did up here with this equation, but I'm going to use the original s of 0 is equal to 80 to solve for this c2, and then I'll have my original position function. So in setting this equation equal to 80 and plugging 0 in for all of my t's, I find that my constant here, my second constant, is equal to 80. So I have this equation down here. I've got negative 16t squared plus 64t plus 80 is my original position function. So something else that's important in vertical motion problems is figuring out when that object hits the ground. So let's find out when that ball hits the ground. So we have our original position function, which is great because all I really need to do is set that quadratic equal to 0 and solve for the times that it is on the ground. So I'm able to factor out a negative 16, which is great because I get t squared minus 4t minus 5, and that's factorable to t minus 5 and t plus 1. So I set those two equal to 0, and I get a positive 5 and a negative 1. Obviously, we have to reject the negative 1 because I can't go back in time. So the ball hits the ground 5 seconds after it was thrown. All right, that's going to do it for this video. Many thanks for watching.